Kia ora koutou katoa, it's Mrs. Goodson here, and this video is part of the organic chemistry videos for Level 2 NCEA Chemistry. This video is about how to name and classify alcohols and the physical properties of alcohols. The next video will be about the chemical reactions of alcohols. So firstly, the naming. You take the E off an alkane and it's replaced with an ol, to give an alcohol. The first one is methanol, and then ethanol. The position of the hydroxyl group, the OH group, must be given in alcohols with 3 or more carbons. For example, propan-1-ol, and propan-2-ol. So you look for where the position of the OH group. And you need to number the carbons so that you use the smallest number. So this is not propan-3-ol, but rather propan-1-ol. That would be a mistake to name it propan-3-ol, counting from the wrong end. In this case, it's propan-2-ol because the OH group is linked to the second carbon. Naming alcohols with branch chains. First of all, you have to name the parent chain. In this case, it's butane. 1, 2, 3, 4 carbons. The branch chain is this one here, 1 carbon, so it's methyl. You number the parent chain so that the OH group has the lowest number. You write the full name as the branch position, a hyphen, branch name, parent name, hyphen, OH position, hyphen, OL. You only need to put hyphens between letters and numbers. So this molecule is named 3-methyl-butan-2-ol. Alcohols with more than one hydroxyl group. These are called polyalcohols. For example, ethan 1,2-diol is used as antifreeze in car radiators. You can see it's got 2 OH groups. So di for 2, and each hydroxyl group is attached to a different carbon, carbon 1 and carbon 2. So we need to signify that in the name. Propan-1,2,3-triol is a common chemical called glycerol, and it's used in hand lotions and in making confectionery. 1,2,3-triol. Alcohols are classified as primary, secondary, or tertiary, depending on the number of carbons attached to the carbon atom to which the hydroxyl group is attached. The position of the hydroxyl group does affect the reactivity of the molecule. For example, write the structural formula for the following to show the 3 possible classifications. So propan-1-ol, you can see this is the hydroxyl group and it's attached to a carbon that is only attached to one other carbon. So it's a primary alcohol. The next example, propan-2-ol, has the hydroxyl group attached to a carbon that is attached to 2 other carbons. So it's a secondary alcohol. Methylpropan-2-ol has the OH group attached to a carbon that is attached to 1, 2, 3 other carbons. So it is a tertiary alcohol. Alcohols have the general formula CnH2n+1 OH. They are saturated molecules. Another way of writing that would be CnH2n+2O. Functional group. Alcohols have a hydroxyl group bonded to a carbon atom. They are saturated compounds with no carbon-carbon double bonds. The carbon atom to which the hydroxyl group is attached has 3 other atoms bonded in a tetrahedral arrangement, and you can show that with this notation here. The bonding around the oxygen atom is also tetrahedral. There are 4 electron clouds around the oxygen. 2 are bonding and 2 are non-bonding, giving a bent shape around the oxygen atom with a bond angle of 109 degrees. Physical properties of alcohols. Alcohols contain polar molecules due to a highly electronegative oxygen atom in the hydroxyl group. Highly electronegative. The physical properties of alcohols are influenced by the hydrogen bonding ability of the hydroxyl group. The hydroxyl groups can hydrogen bond with one another and with other molecules. Hydrogen bonding raises the boiling point and lowers the solubility of alcohols. This is a form of intermolecular bonding. It is the strongest form of intermolecular bonding. These diagrams show the hydrogen bonding between molecules. It is the strongest form of intermolecular bonding, but it is nowhere near as strong as the covalent bonds holding these molecules together. This is how the hydrogen bonding affects the boiling points of alcohols. The red bars show alkanes, and as the number of carbon atoms increases, the boiling point increases as the intermolecular forces between the molecules increases. However, this shows that the number of carbons also increases the boiling point of alcohols, but the boiling point of alcohols is much higher than the boiling point of alkanes. And the reason for this is the hydrogen bonding, the intermolecular forces or attractions between the molecules. The boiling point of an alcohol is always much higher than that of the alkane with the same number of carbon atoms. Between alkanes, the presence of van der Waals forces, also known as temporary dipole-dipole interactions. Between alcohols, there is also temporary dipole-dipole interactions and permanent dipole-dipole interactions, but there's also this hydrogen bonding because of the oxygen being very electronegative. It takes more energy to separate the alcohol molecules than it does to separate the alkane molecules. Therefore, the boiling point of alcohols is higher than alkanes. The boiling point of the alcohols increase as the number of carbon atoms increase. Alcohols with lower number of carbons have a smaller size compared to alcohols with higher number of carbons. The smaller size have weaker van der Waals or weaker temporary dipole-dipole interactions instead of hydrogen bonding that is formed between the OH group. Therefore, alcohols with lower number of carbons have lower boiling points. Solubility. Alcohols dissolve in water because hydrogen bonds form between the polar OH groups of the alcohols and water molecules. Water is also a polar molecule. Therefore, it can form these hydrogen bonds. The first 3 members of the homologous series are soluble in water. So that would be methane, ethane, and propane. Those are the alkane groups of the homologous series. So those are non-polar. The ones that I'm supposed to be talking about are the alcohols. So we've got methanol, ethanol, and propanol. So they are soluble in the water because they've got the polar OH groups that the alkanes don't have. However, the solubility decreases as the chain length increases, and the larger part of the alcohol molecule is then made up of a non-polar hydrocarbon chain. So the larger alcohols are not soluble in water, and it doesn't form these hydrogen bonds with water. Small alcohol molecules is methanol, ethanol, and propanol, and they're miscible. They are soluble in water because the hydroxyl group wins out over the short carbon chain and forms hydrogen bonds with a water molecule. Butanol with a 4 carbon chain is moderately soluble. Alcohols of 5 or more carbons are effectively insoluble in water because of the hydrocarbon chain's dominance. In an exam question, you may be asked to look at some data and explain it. You don't need to remember the exact solubility data in this table, but just remember how to explain the trend. It's because the smaller molecules are more polar, and so will mix with the water and form hydrogen bonds, whereas the larger ones have a large non-polar hydrocarbon chain. So we say that this hydrocarbon chain is the hydrophobic region. It's scared of water, it's hydrophobic. Whereas this part of the molecule is hydrophilic. It loves water and it can form hydrogen bonds. So that is the end of this video, which is about alcohols, how to name and classify them, and the physical properties of alcohols.